And please be noted that our test will be tomorrow, okay? Okay, tomorrow night, tonight. Tomorrow night, 9 p.m. And for those who have maybe some difficulties in terms of maybe electricity, because we know that some part of our peninsula Malaysia is in a very worse condition due to the flood. For those who have difficulties, you can inform me, just WhatsApp me personally, so that I can forward this matter to our coordinator. Okay, so if I haven't received any what call information, then I assume that all of you are okay with the test. Okay. Okay, so today, okay, so for today, we will continue on the Shunt series and also separately excited Decimoto. Okay, so first we go to the Shunt connected Decimoto. I have already pre-recorded this video and upload into the YouTube. And I think for those who have watched that, then it's okay. You can also watch this presentation. Okay, so this is Shunt Decimoto. As you can see, the field circuit here, okay, this field circuit is currently connected. Sorry, this whole field circuit, okay, is currently connected in parallel with the armature circuit. So this is your armature circuit. So connected parallel. So that's why we call this one Shunt connected DC motor. And for those who maybe have not watched the video of the Decimoto, so actually we have two circuits. The first one is the field circuit and the second one is the armature circuit. So the field circuit, this one is actually represent the stator winding. Okay, the stator winding where the objective of this field circuit is to produce flux. Okay, because we know flux is a very important parameter, because without flux, we cannot get the back EMF, and also without flux, we also cannot get the torque, because as you can see, the torque is the production between the interaction of the flux and also the current armature here. Okay. So, and then the second circuit, the armature circuit, this one is actually represent the rotor, okay? And this is your RA, which is represent the internal resistance of the rotor, and this one is the back EMF, okay? And back EMF, this is a voltage that induced due to the rotation of the motor, okay? And so in shunt DC motor, okay, the parallel, this one, okay, and then we have the R adjust to actually you can adjust this resistance to adjust the value of the IF, and when you adjust the value of the IF, definitely you will actually adjust the IA and also IL, because right now the equation is IL is equal to IF plus IA. So if you change anything, IF or IA, so definitely all the current values will be changed. Okay. And this is the power flow of the shunt DC motor. So we have the power input, which is a VT multiplied with the IL. Okay. And then we have the losses, which is the field losses. So this is related to the field circuit. And then we have the armature losses. So P in minus these losses, you will have the power developed by the motor for the mechanical. Okay, where the power developed is actually is the output side at the output side here. So IA multiply with EA. Okay, so this is the power developed for the mechanical, and also you can use the mechanical equation um, to calculate the power developed, which is from here is actually T developed multiplied with the speed in radian per second. So this speed must be radian per second, and this one must be in Newton meter. Okay, and then you have rotational loss. So this is mechanical, which is not be covered, but maybe for if there is a question, then maybe we just give a value. Okay, so this is a mechanical part. So these losses must be developed minus the mechanical losses. So you will have the P out, which is T out multiplied with the speed. And as you can see here, um, the power output and power developed, as you can see, the speed is actually still remain the same. The only difference is actually on the T torque developed and torque out. Okay, so actually torque out is actually equals to T developed by the electrical motor minus the torque roto loss. Sorry, rotational loss. Okay, rotational loss. Okay, so you will have the torque output. And this is the torque speed characteristic. And I think this is important characteristic for the Decimoto type. Okay, so you need to know the torque speed characteristic of each Decimoto. Okay, so for Shunt series, so there are different characteristics. So how to derive this torque speed characteristic? This torque speed is actually what you will actually plot the torque versus the speed. Okay, so to obtain this relationship torque and speed, we go for from this equation. We start from this equation. Okay, this is actually from the armature circuit. Okay, and we already know that torque developed is equal to K flux IA, and we rearrange this, so you will have IA is equal to T developed over K flux. Okay, and then you use EA is equal to K flux speed. So you substitute IA here and also EA here. You will actually have this equation. So right now, this armature circuit can be as has been written in torque equation and also speed. Okay, so you will have this one, and as you can see, this is a linear equation where it's actually represent such as y is equal to mx plus c. So if we expand this one should be negative k flux square over Ra speed plus k flux Ra Vt. Okay, so this one is your m, your slope. Okay, so this is your y, and omega is your x, and this is your c cross. Okay, at y axis. So if I plot, so you have a negative slope. So I plot here. So this one will be your C, okay, where the speed is 0, okay. So starting from here, the torque is very high, and when the speed is increased, the torque will actually reduce, okay. So this is actually where this is what we call the no load speed. This is happen when the torque is 0. Okay, so this is the characteristic of the shunt Decimoto. Okay, the starting torque when the speed is 0 is equals to this value, K flux over RA multiplied with VT. Okay, and then when the speed is increased, the torque produced will actually reduce. Okay, and if the load is, if the torque is 0, so the speed here we call as a no load speed. Okay, so this is the stall torque. So this one, the name is stall torque. This is actually the starting torque actually, and the no load speed here. Okay, and usually we operate our motor from this point. Sorry, from this point. Okay, the motor speed is always arranged from not very far from the no load speed. Okay, we have finished on the shunt Decimoto. The second one is the separately excited Decimoto. So as you can see here, the field circuit, and then this is armature circuit. I don't know whether my spelling is correct. Oh, AR. Okay, is actually separated. The circuit is supplied with using separate DC source. Okay, so that's why the name separately excited DC motor, meaning that IF and IA is no longer connected. Okay, so they are independent of each other. So meaning that if you increase IF, there is no change on the IA, unlike the shunt. Okay, because we know the shunt is actually IL is equal to IF plus IA. So definitely, if you change IF, it will affect the values of IA and IL. But for this separately excited DC motor, when you increase IF, there is no change of IA. Okay, because field circuit is just to use to produce flux. Okay, so the armature and field circuit is independent to each other. But the torque speed characteristic, when we do the derivation, finally the torque speed characteristic is similar to shunt DC motor, which is like this. Okay, which is very similar. Okay, so we have finished on the shunt and separately excited DC motor. So we go for one example, 50 horsepower shunt connected DC motor. So as shown here, has the magnetization curve. So the magnetization curve of the DC motor is actually the relationship between EA and IF. Okay. The DC supply is VT is equal to 240 volts. Okay, 240 volt. The armature resistance is 0.065. The field circuit is 10 ohm. And the R adjust is 14 ohm. At a speed of 1200 RPM, okay, this is just information. The rotational loss, this is actually mechanical loss. Okay, this one, mechanical loss, given 1450 watts. Okay, meaning that P out is equals to uh, P developed minus P rotational loss. Okay, where P developed is top developed, sorry, multiply with the speed, while P out is T out multiply with the speed of the motor. Okay, where T rotational loss, the torque is equals to the torque of developed minus torque output. Torque output. Okay. Usually torque developed is much higher than the T out because of the losses. If this motor drive a hoist that demands a torque of T out 250 Newton meter independent of speed, meaning that this motor is connected to a load that have a torque of 250 Newton meter independent of load, meaning that your load is a constant load. Okay, 250 regardless of the speed. So mean that it is constant. We have torque load that is a proportional with the speed. We have torque load that is quadratic with the speed. Okay, so we have three types of load here. This load, this motor is connected to a constant load. Okay, so independent of the speed. So right now, determine the motor speed and also the efficiency. So determine the motor speed. How to determine the motor speed? So actually, the motor speed is actually related to, we know actually, we have equation which is VA is equal to IARA plus EA, right? And we have also AA is equal to K flux speed, and also we have torque developed is equal to K flux IA. So actually, and then another one is the P develop. P develop is torque, which has been shown here. Okay, torque develop multiply with the speed. So actually this is actually the equations that relate in this calculation. Okay, so from here, what can I see is actually the speed is related to EA, the back EMF, the voltage induced. Okay, so right now, from the magnetization curve, this is the, when IF is equal to 14, it will give a voltage of, induced voltage of 312. This is when the speed is 1200 RPM. Okay, but right now we didn't know what is the speed. Okay, what is the speed? We can use this equation. E during 1200 is equal to over E at the X, we don't know, the speed is equal to 1200, right? Over the speed that you don't know. So right now, we didn't know two variables, the voltage induced and the speed. Okay, so the question is actually to obtain the speed. So meaning that you need to obtain first this EA. What is the voltage induced at this speed? Okay, from that, then you can get the speed. Okay, let's look at the solution. Actually, I have already shared with you in the WhatsApp group last week. Okay. Okay, let's look at this solution. I think you can also look at the solution. Okay, so right now, we don't know the IF. Okay, so the first one is actually to obtain the IF. So from the equation, so IF is equal to VT over total of the resistance, so 10 ampere. Okay, and then from referring to the magnetization curve, if IF is 10, so the voltage induced is around 280 volt. This is actually during the speed 1200 RPM. Okay, so from that, it's actually our intention is to get the EA, okay, the voltage induced at the speed. Okay, with that we don't know. Okay, so from here we can obtain the equation, the formula. Sorry, the K flux values. So the K flux values, which is from EA over speed. Okay, so the speed is 1200 RPM. You need to convert into radian per second. So we have the K flux is equal to 2.228. Okay, and we know that T developed is equal to K flux IA. Okay, and T developed is equals to T out plus T rotational loss. Where the T rotational loss given that at 1200 RPM, the rotational loss, power loss is 1450 watts. So from that, you can obtain your torque rotational loss, which is 11.53 Newton meter. After you obtain this rotational loss, you sum up with the T out, which is 250 Newton meter. So the T developed is actually 261.54 Newton meter. Then from that, you will obtain the IA from the equation T developed over K flux. So the I amateur that flowing is 1100 and 117 ampere. Okay, so after you have obtained this one, so finally the back EMF induced is 232.4 volt. Then from that, you use the equation of the speed and torque, speed and also back EMF. So finally, you will obtain that the speed of the motor when supplying the load of 250 Newton meter is around this one. Okay, so or 995 RPM. You can also use the equation of, for example, E 1200 over EX. So this one is 1200 over speed that you don't know. But right now, our EX is, we have already obtained 232.4, and E at 1200 is given in the graph, which is 280. Okay. So 280 over 232.4. So 1200 over x. So you will have your x is equals to 1200 multiply 232.4 over. Okay, you should get your x is also similar 996 RPM. Okay, so you can either use this equation, the relationship, or you can also use these equations. It's up to you. Okay, so this one is actually, this equation is actually E1 over E2 over the speed of E1 and the speed during E2, N2. Okay, and the efficiency is directly P out over P in. Okay, so P out over P in, so T out multiplied with speed over the P in is actually in electrical parameters. Okay, so you need to calculate your I total, which is IL. IL is IA plus IF. So your IA is 117 and your IF is 10, right? So that's why you have 127 ampere here. Multiply with VT. Okay. So that's why, and then your T out is actually your load, which is 250. The speed is actually need to be in radian per second. Okay, don't use RPM. You need to use in radian per second. So the answer is 85.5. You can also use P out as a IA multiply with EA over VTIT. You will have the same answer. So for example, IA is 117 plus the EA induced is 232.4 over 240 multiplied with 127. Okay, you should receive this one. How much? 117 multiply with 232.4 over 240 over 127. Oh, this one I got around 89. I don't know, 89%. But maybe this one 250 over 240. Actually, should be the same. Should be the same. Maybe there's some numbers here that is actually the numerical value here, but actually the same. But if you use IAEA to calculate your P out, then it's actually okay. I accept it. Okay, don't be quite scared. Okay, if I see that you are understand, I can see that you understand, then I just give marks. Because we know in engineering, the mathematics, for example, some values here, maybe you round up, will actually affect the final answer. Okay, so I hope you understand about, because this is quite complicated because you have rotational loss and so on. But actually, it's actually the same. Actually, this one, okay, is actually originate from all from these four equation here. Okay, and also one more is actually VF. VF is equal to IF RF. Okay, one more. This is for the field circuit. Okay. And then the last one is the series connected Decimoto. So as you can see here, the field circuit and armature circuit are connected in series. So meaning that IA and IF are similar. Okay. So the torque speed characteristic. So the same, you need to, this one, just to mention to you, this is the tips, okay? Just to mention to you that this series connected DC motor will be in your final exam, okay? This one will be in your final exam, but it is only a theory questions only. So there is no calculation. But I don't remember what is the theory is all about. Maybe you need to sketch the connection of the series connected Decimoto. I don't know. Or maybe you need to derive the equations about the torque speed characteristic of the series. Okay, so please be noted. So actually, the torque speed characteristic to derive it is actually first, it's actually come from the armature circuit itself, RA plus EA. Okay, and currently we know that this is a series. IA is equal to IF, and we know that the flux is proportional with the IF. And if we want to actually remove this proportional, so what you need to do is actually to insert a constant here, okay, K. So, and then as we already know that IF is IA, then you can actually um, substitute IF with IA. Then you rearrange this one is IA is equal to flux over K. Then you insert this into this, and EA also you need to, uh, okay. So actually the same thing. So you calculate this and so on. Um, okay, for example, this one flux. Okay, sorry, this one K flux is equal to KFIA. So what you need to do is substitute this formula into this EA and also torque. Then you will have this one. Okay. Oh, sorry. This one should be plus RF. Okay. RF. Sorry, IFRF. Okay. Because this is series. This is the equation. Okay. Sorry. Plus IFRF. Okay. This one. Then from here, you substitute this one into flux here. Also here. And then you will obtain this relationship. And solving for IA, so meaning that you rearrange this equation, you will have like this. Okay. And then finally, by using some modification and so on, this is the torque versus speed characteristic of the series Decimoto. Okay, so as you can see, this is a quadratic equation. So meaning that you will have this torque speed, which is in a quadratic. Okay, so the solid line here showing the uh, theoretical equation of this formula. So what is mean that when the speed is very, very high, you will receive that the torque is actually is actually is actually zero. Okay, but actually okay, sorry. Okay, when the torque is zero, okay, based on the equation, when the torque is almost zero, they said that from that equation, the speed will be very, very high. Okay, so it is crucial, or it is should be in a safety measurement, whether when you disconnect this series motor, okay, please do not disconnect directly, because it is will have actually the motor will actually rotate at very high speed, and it is maybe very, very dangerous. Okay, but usually for practical, there is what I call losses and so on. So usually when the torque is disconnected, when the load is disconnected, the speed is will be actually towards zero. Okay, towards not zero, towards a very what I call low value of the speed. Did not be infinite value of. Okay, so this is the solid line where it state that when your load is disconnected, meaning that zero load, zero torque, this motor will run at very high speed. Okay, but this is not happen in practical. But for safety measurement, uh, please be noted that if you want to disconnect load, so you need to actually connect to something that actually you, in other words, this series Decimoto is not appropriate to have a no load condition. Okay. If you want to remove it, then you need to have some safety measure. Okay, so one example of the series connected Decimoto. So a series connected Decimoto run at 1,200 RPM while driving a load that demands a torque of 12 Newton meter. Neglect the resistance, rotational loss, and saturation effect. Find the power output, then the new speed and output power if the load torque increase to 24 Newton meter. Okay, so this one is actually find the power output. So this is the power output. You just need to find torque. Okay, the torque produced, because the torque produced, the torque output must equal to the torque load. Okay, so 12 Newton meter multiplied with the speed in radian per second. So this is the output, 1,507 watts. So, and then the second question, find the new speed and the output power if the load torque increased to 24 Newton meter. So if the torque is increased to 24 Newton meter, and we already know that for series Decimoto, the torque and speed is actually the equation, the relationship is actually torque is proportional with the inverse of the speed square, which is this one, right? From here, torque, speed, which is square. Okay, so you can use this formula, T1 over T2 is equals to omega 2 over omega 1 square. Okay, so this is the old torque, this is the new torque. So you use this equation. So the new speed is in RPM, because we are using RPM here, 1,200 RPM here. So 848 RPM. And then the new torque, the new power output is just multiply torque multiply with the new speed. So which is what 2131 watt. Okay. So for this is for the series circuit. For the sorry, this is for series, and then for shunt and excited Decimoto, the torque is proportional with the speed. Okay, because the torque speed is linear. So if you want to use, so T1 over T2 is equal to omega 1 over omega 2, right? Okay, but for the shunt, so it's different. Sorry, for the series, so it's different because it's a quadratic. Okay, so I think that's all for today. This video is pre-recorded. I think pre-recorded, yes, pre-recorded. After this, I will upload inside the YouTube and so on, so you can refer back. Okay. So for next week, we go on this one, speed control of the Decimoto. And next week is the last week for this subtopic. Then we go for the AC motor. Okay, if there is this slide, I think I have shared this slide. I think I have shared this slide. Okay, it's actually one note only inside in the WhatsApp group. Okay, maybe I forgot to upload in the e-learning, but I will check it again. Oh, okay. I will send to you. Okay. So for the test, please be remembered tomorrow, tomorrow 9 p.m. And okay, is it hard or is it difficult? Okay, so for question number 1, which is the coal, it is very simple and straightforward. I think if you refer to the examples from my notes, I think you are able to answer it. Okay. And another one is about the okay. And then I don't know the arrangement of the question, but for the coal power generation, just use the example and exercise from my notes. Okay. And for the second question, which is the single phase transformer. Okay, so single phase transformer, there is no short circuit test, open circuit test. Okay, that one it will be test inside during your final exam. Okay, the only question that for single phase transformer is the equivalent circuit. Okay, referring to the secondary, meaning that you have been given a value. Okay, R1, R2, RC, XM, and so on. You need to transfer it into a secondary refer to the secondary. What is the circuit when you refer to the secondary, which is I have shared with you I think last week. Okay, because I forgot to actually to teach you about RC, what RC and XM, what happened when RC and XM is transferred to the secondary. Okay, and then there is no phase diagram. There is no phasor diagram sketch and so on. So we actually exit that one. So we not be tested. So after you have obtained the single phase equivalent circuit when refer to the secondary part. So and then next is actually to find the voltage regulation and voltage efficiency. Okay. So voltage regulation and voltage efficiency. you just follow what is inside the slide, the equation and so on. Okay. So what else? And then for the transmission line, so it is T line medium, T line, but the equation of the ABCD parameters, the matrix, will be given. So you don't need to memorize. Okay. So from that, you need to calculate what is the voltage regulation and voltage efficiency and the efficiency of that medium line. I think it is straightforward. Okay, if you follow my slide, you do the exercise, I think there is no problem. The problem may be on the uh, what I call some mistakes that usually students do. For me, I also sometimes do it because careless mistake. Okay, sometimes the numbers point 0.02, you put 0.2, so that is the careless. Okay, I think not very hard, but I'm agreed that for this test too, the topic is quite big to be covered, but we just follow the coordinator decision after we have discussed and so on. Okay, habis pukul berapa the test will actually similar to test 1 hour something. Okay, so and then I will give you around maybe 20 minutes to upload. Okay, so for this test too, I don't know whether I want to use e-learning or Google Form. I think 1 hour plus, I think. I don't remember. It's actually similar to the test 1. Okay, I think Google Form. I think I agree with you. Google Form is very light. Okay, sometimes e-learning very heavy to turn to actually to log in and so on. So I will I will use Google Form. Okay, but actually, if you are using e-learning, it's good because the marking will be displayed to the students. You can actually know, you can actually see your marking. Okay, that is the advantage of using e-learning. After I give marks, then you can see automatically you can see my marks. Okay, but by using form, yes, I cannot give you the papers. You need to personally request from me, then I will send it to you. So the test will be synchronous, just like test 1, meaning that you need to turn on your camera and so on. Uh, Kalau internet tak kuat tu is actually that's one yes, I know, I agree, some internet connection and so on, but it's okay. We just follow the SOP. If you have some problems with the internet connectivity and so on, you just inform me as soon as possible. Okay. Okay, so okay, for the assignment submission, yes, you can submit your assignment by today. By today, okay, I will turn on the link. Okay, I think this one week 13, right? 13. I think okay, week 13. I will on the link. Okay, never mind. But please give me some time. Maybe tonight you can submit. Okay, because I have several things that need to be done after this. Okay, by today you can submit. I will turn on, or maybe I will actually. Okay, and then what else that you want to ask? So Shunt. So okay, I post you the Shunt Decimoto exercise. Okay, and then next week also DC generator. Okay. Okay, if there is no question anymore, so then we dismiss this class and just buat mind macam ni. Yes, yes. For the second assignment, just buat mind map. Yes. But I don't know whether Google can actually insert the video link and also on, but I don't know. But if you can make it with the video is embedded in that Google, then that is very good. But if you can embed the video, then it's okay. Or maybe you can just give the link. I don't know. No, no, no. You can submit by today. You can submit by today. I will open it until week 15. Okay. Assignment you can submit by today, starting today until week 15. Yeah. Is it? I think this one week 14, I think. Week 13. Next week is week 14. Yeah. Saya awak menakutkan saya ni. Kita ada AC motor ni susah nak cover ni. Okay. Okay. Okay, thank you very much. So we dismiss our class, okay? Okay. Assalamualaikum and have a very good day.